Hello, in this video we're going to continue our project in emulating a CPU using Zig. So there are some things that, so in the last video we did implement a simple CPU that had registers and it can do some stuff on its registers. We had some instructions for small simple mathematical operations. For setting was just setting a register to a certain value. We also had add for adding numbers together. We had sub for substituting numbers, not substituting, subtracting. We have division, multiply, and power, right? But there are problems with this. So what is the problem? Our CPU is actually much smarter than it needs to be. Why? So the reason is that a CPU, an actual CPU, cannot differ itself between what is in a register. So a CPU, so basically our registers are just 64 bits unsigned integers, which is basically, let me just change this comment to a more reasonable one. So this is basically a 64-bit integer value can be either a reference to memory or a value itself, right? Also, so let's actually write some to-dos for ourselves. So I'm gonna write to-dos in here. So, and I actually did a simple commit to just move everything from main into all CPU stuff into a CPU file. Just this, nothing changed. So our to-dos is going to be, first we need to make CPU agnostic about stuff in a register. Each instruction should behave different. Should infer that for itself. So each instructions, we might have instructions that operate on memory addresses, and we might have instructions, for example, for adding and stuff that operate on the actual integer inside a register. So basically, I mean, the concept of pointers is not that valid inside a CPU. We cannot we cannot differentiate between a pointer and a number, because pointers are numbers as well. They're basically the number of this memory segment we have. So if you remember, we said that our memory is a slice of U8s, slice of bytes, 8-bit integers. So basically each memory byte or bit or segment is just 8-bit integers, right? So this is 1, 2, 3, 4, 5, 6, 7, 8. 8-bit integers, each memory, and then we have the next 8-bit. Right, this is basically our memory, how it looks. So it's an array of bytes, 8-bit unsigned integers. So 1 gigabyte of memory is basically 10 to the power of 9, an array of bytes. Also, there's another thing. So our memory is also so smart. We don't have memories that are this smart. So first we need to make our CPU agnostic about stuff. Second, and we will talk about memory, but let's finish the CPU to-dos. Also, CPU loads instructions from memory. So now the way our CPU works is by basically passing a slice of instructions into the run function. That's not how a CPU works. A CPU does not have any, it's not a function. We need to put instructions inside memory and then ask the CPU to run the instructions. So we need to load the instructions from memory. Also, our memory parts. So our memory, so we have both stack and heap are on the same memory space. And this is also the job of the CPU to know where to look for the stack values and where to look for heap values. Let me put this to do actually inside the main file. So this is our to-dos. We need to do these first. After these, we will go further. But we need to fix these. So let's start with the CPU. So we should make our CPU agnostic about register stuff. And so for start, what I'm going to do is so I'm gonna assume from now on that these instructions we have in here are going to work on a register. These are register instructions. So if I add something to the value inside the register, I don't care if it's a pointer to a memory or just the value itself. It's not important for me. I'm just gonna add number to it. But this is also true for subtract, division, multiply, and power. Okay, so so a register can basically become a simpler thing. A register is nothing but a U64. So registers are basically an array of 16 of U64s for a 64-bit CPU. Let me have this comment in here, and let me just remove this. Right? So we have this. So we also have so now our code is going to fail very bad because our ref in instructions is also going to just be a U64, not two values. So I'm gonna do this and do this. It is also going to fail. I don't know why my zig ls thing is not running. Language server start. Why? Okay, so what's wrong with you? Connection is already lessening. Okay, let me just pause. Sorry for the disruption. So the ref we have is going to be okay, so the ref is going to be okay, so refs are going to be U64s as well, right? Maybe we need to have a constant for CPU register. No, just have the U64s. And these are going to be, so let me just do this. So let me just replace every ref with U64. So better. So we have the instructions and okay, so this is instructions are okay. Now let's come here. So we have the run, and each so we are going to not switch anymore on these, and I'm gonna just use the so what is this? So instruction.out, which is a register, right? So it's a register number, okay? And it's also a U60. Okay. I'm gonna model this as also as U64 because not necessarily we want to put an operation output inside a register. Maybe we have some operations that are going to work on U64s. So I'm gonna copy this, paste this in here, paste this in here, paste this in here. Okay, I missed some. Can I do this? Also, in here, I'm going to do registers is S16. Yes, it's okay. And instruction.argument. So for set, it's simpler. I'm just gonna set this value to the value inside the register 1, right? So what is inside the register? It's just instruction.arg1, and I'm gonna delete these lines. I don't have this args anymore. This args resolving, because my out register value becomes basically self.registers hence.arg1 same goes for this. I'm gonna copy this. Okay, it's just going to subtract. Paste. Also this. Okay, so now, let me just fix the operations. This is division, this is multiply, and this is power, which I think it was in std math. What was it? Why my autocomplete is not working? Let me just check this. Okay, so now I think it's working again. So std math power, I think. So it was returns x raised to power of y. So I have u64 stuff, and the first one is going to be this, the second one is going to be this, and done. Let's format this. Oh, we don't have formatter for Zig. Weird. I think there is a Zig FMT thing, but I don't know. It's not always a register number anymore. So now let's see if we can run the code. So this is of course wrong. So instruction.set. So set has an input reference. It's not a reference anymore necessarily. It's just in, or let's just say value back in here. So setting, just set 10, also 10. So add also gets two values, which are argument 1 and argument 2, both register numbers. So I'm gonna just do 0 and 1. Register number, register number, register number. So and for subtract, okay, so for subtract we have also value. So for example, for subtract, this is not the case anymore. We cannot do thing we were doing. Let me just do this, and to make it more readable, one-liner now simpler. Our lines are smaller now. Okay, so we have these instructions: set 0, register 0 to 10, register 1 to 10, then add register 1, then add register 0 and 1 and put this result into 1, add register 0 and So add register 0, and this is not power, this is for power, and we don't have anything in register number 3. So what I'm going to do is to add an instruction to put value of 3 in register 3, and use this, subtract this with value is this. Okay, a bit better. So and put the register, this is not a register anymore. So if we do this, it's already in register 2, and if we subtract this with the register 2, this should be 0, right? So yeah, oh, I already did some to-dos in here, but let's just ignore this and ignore this test. I'm gonna actually write tests before doing anything else. So let's just try to run this. Zig build, zig run. We get error because in CPU.zig line 93. Oh, why I did copy paste this one? This is wrong. This is completely wrong. We don't have value anymore. We just have data. We don't have any kind of enum or anything. Can I do this? No. Can I do this? Remove this, remove this, remove this, remove this, remove this. Okay, this, and I should do math thing. std math power u6. I'm doing u64 stuff, and this. Okay, run. We got error because of the std debug print of yes. What's the error? Reg dot value? Is there reg dot value anywhere? Yes. Registers state. Okay, so we got the opcodes. Oh, nice. So I'm going to set the register 0 to 10, register 1 to 10. Then I'm going to add register 0 and register 1, putting to 1. Register 3, I'm going to set register 3 to be 3, and then I'm going to power register number register 0 to, okay, I'm doing a after which operation after the power, after the sub. I cannot display these. Is this the problem in here? Can you give me where or what line? So the power, that might be true. The power register number 2, which is actually no one. So register number, okay, that's okay, because we didn't put anything in register number 2. It's okay. In register number 0, we have, in register number 0 we just have 10. In register number 3 we have 3, so it's 1000. How we have the overflow? Okay, what's that sound? Sorry for the disruption. So You couldn't print any of them. Let me just not do this, right? Make it simpler. Okay, we also have the integer overflow here, so we have a major problem because this code is really simple. Is this the problem? Let me see. So I got the instruction to display the instructions, okay? Then I do run, okay? So let's just do for one. Let's see if it can run. Okay. So set register 0 to 10. Oh, we didn't. Okay, that's the problem. Basically, our set is not working. So why our set is not working? Because set self register instruction out into self that registers instruction argument 1. So you know what? Let's just do a print in here. std debug print. I'm gonna say these two values. Isn't there a print line thing? No, I think. So I'm gonna say instruction.out and instruction.arg1. Oh, for the set is not based on register. Set is just this. That's the problem. I don't need debug. Set now should work. Yes, that was the bug. That was a stupid bug. These should work now. I hope so. Let's run. And we got this, which is really nice. Nice. Okay, I'm back. So we get everything working again, which is cool. I'm gonna write tests before doing anything more. So let's just write some tests. Basic set should work. What I'm going to do is just have a simple instruction set, which is just setting something, and I'm gonna do cpu.init and try to run the CPU, right? And finally cpu.registers 0. Is there an assert or anything that we can use? Let's just open the Firefox. So zig test. Let's see. Zig language reference. Is there a section for testing? Test. Test. How you don't have test? Oh, okay. Can I do? I mean, what? Oh, try expect. What is expect? Okay, std texting expect. Let's just use this. So let's just say that I want to say std.testing.expect equal expected is. Oh, look at the type signature. It's so nice. It says expected can be any type, but actual should be the same type. That's really powerful in Zig type system. It's really powerful. Okay, I mean, you can basically reference the parameter before you. You can just use the metadata of the compiler about that parameter. So what happened? I don't know. So I'm gonna say CPU that registers 0 should be 10. Is this 10 U64? U64 10. Close this. Okay. If I do zig run test, sorry, zig build test, expected type found U64. Should I say 10? Expected comp time int found U64. How should I specify this? Should I do this? Expected function found type. No, not this. I muted all notifications so we don't get disruptions again. So we got another one. Oh my god. Okay, so what should we do to fix this? Expect equal okay. How can I cast types? Basically say this as this. Where is the as? Oh, comp time and an expression. So can I do as U64 error is ignored? Yes, we should now do a try and this should be okay. Yes, so our test pass, which is nice. Okay, let's continue. Sorry for disruptions. So our set, so let's just call this test or just say set. Now I'm gonna test another instruction, which is add. I'm gonna have the same code base for add, and we're going to have add of register 0 and 1 and put it in 2, 0 and 1. Okay, cool. So now register number 2 should be 20 because of adding of these. This test should also pass. Let's go for the next one, which is the, and you know, since these instructions are atomic, we can just, you know, test them by one. At least these instructions are really simple. So sub, we have the same thing, maybe just make this a bigger value, and now the sub works. Put the result in register number 2, and 2 should also be 10. So now this should pass. Okay, I don't know what's wrong. So it's set failed. Why failed? Expected 20 found 1. Oh, yes, found 10. Right, this should work. Okay. Sub. We got add, we got sub. Okay. So now let's go for null. And let's just do them all at once. So 20 and 10 would become, if we do an operation between them, should become 200. And do another one for division. If we do this, should become 2. And finally, for the power, this should be, so the power of 10 is too much. Let's just do it 2. This should be 400. Let's just run. All tests should pass. No, because we had this. Okay, for multiply 20 and 10, if we multiply them, we probably have this. Oh, we didn't do this. So this is multiply, this is division, and this is power. Now hopefully, what did I do? Hopefully everything should work. Yes, which is nice, and we basically don't need this main function anymore. We can just comment this out. Okay, so we actually did write some tests, so some test instructions. So at least now we know that our CPU is, we can test it, because the changes we are going to do are a lot. So we did the first one actually. Let's go for the second one, which is hard because we need to first fix the memory. So let's just remove this stack thing and actually put memory inside the CPU module. The memory is just a count time int, count time size, which is int, which is u64, yes, and this will just return a type, which is a struct. We have internal, we have data, which is, so memory is a array of bytes, u8s. So size is basically, so if we say, for example, we want a 1 gigabyte of memory, any size they give us, so size is basically length of array of bytes, again u8. So basically we could do size of u8. Now we're going to have some methods on this public function. So there is going to be a stack inside this memory, right? And there's also going to be some heap. So first time, so for the first thing I'm going to do, it's is get ref. Get ref is going to get a reference to self. Self and a reference, which is a u64. The return type is going to be the return type is going to be, so each so each number basically points to a byte on the memory, right? So we do u8, right? We should say return self data ref. This is just one ref. This is just basically one chunk of our memory, or 1 byte. But we also can do from function get ref range, because most of the times basically a CPU should get a range of values, not just one. So it should be a start, which is a u64, and end, which is also a u64. And I'm gonna return what I'm gonna return. Can CPUs do that? actually I don't know. I don't know if this instruction is actually valid in the context of CPU, or how do CPU chunk memory. Let's not do this. Let's just do 1 byte for now, just 1 byte access for heap. So basically this is like heap access, and actually 1 byte is a large, not large actually. I mean, you can just put a character in here. Unicode, I think Unicodes are get 1 byte for each character. So also I'm going to do is, okay, so there's a stack. So stack pointer, or stack cursor, which is a U64, points to 1 byte, again 1 byte of the memory, and we can say pop returns a U8. We also have push, not returning a U8 but gets the value. These all get self. This also gets self. It also gets a value which is a U8. Yeah, not U8, which is a U8. Yes, 1 byte of data. We can just add 1 byte of data. And we have pop, push. I think that's it for the stack. We can just go up and down. So what is the default value for the stack frame? I'm going to use 0. So stack starts from the start of the memory, and I'm going to do the heap from the end of the memory. And push, oh, it's void. And push, so what does push do? So push basically adds 1 to stack cursor, adds 1, and then in that place puts the value. Pop, what it does is self.data, self.stack cursor, then it's going to self.the decrement 1, and then return value. So this is nice. Can I do format? No. Oh, I always forget that I don't have formatting access, formatting working in VS Code. So I think this is basically our memory. So let's see. Maybe you should write tests for it. And actually, let me first of all put all these tests for CPU inside the CPU module itself. Okay. Tests. Oh. So let's just do. There are ways we can enable these, but test. I think I should root at import now. Does this work? No. Yes, cool. So basically the way that Zig does this, or through its build system, and it says that to execute test, just run test. So basically there is a command called zig test, which you can run for it, just single file. and it says basically just run the zig test. I don't want this in here. Run zig test for file main. So that's basically what it does. And so I need to import other tests inside. Basically, if I import something, I'm importing the tests as well inside the CPU.zip file. Okay, so we put our tests in here. Now let's write some tests for memory. So test memory put push and pop from stack. So I'm gonna do this, and so what I'm going to create is probably a variable of memory, which is memory. Size is going to be 10, just 100 bytes. Who cares? Instantiate this. Now I have my memory. I can do push and pop to the stack. So I'm going to push data to the stack, value 1, and then I'm going to pop that back. And this std testing expect that this is equal to 1. This should now run. No, because we don't have the data field. Data is should also start undefined. Start. Do a try. And it passes because the push and pop works. But if I do 2 pushes, okay, so let's not do this. If I do first, there should be number 2 and then 1, run, it also passes. And what if I add another one of these, but and put 3 in here, but do this in here? So pop should give me the 2 in here, pop should give me the 3, and then pop should give me the 1. Right, so memory stack is working, which is nice. Now let's go for the heap. Memory heap test. So what I'm going to do for the heap, also I need a set ref. So self at the point I'm going to tell you put this value, put this byte. It's going to be a void. So I'm going to do is self.data ref equals value, return. So let's create a memory with just 100 bytes. Okay. So this is actually tricky because I wanted my heap. Let's fix this. So I wanted my heap to start from last. So I'm gonna basically minus that. Yes. So what I'm going to do is to subtract this from the size of the data. So self.data.len minus the ref is the actual ref. Same goes for here. So if they say number 1 in the reference, number 0 in the reference, they mean the last number of on the heap, on the memory. So I basically I behave with the heap, I behave with the memory for the heap operations from the end. So data.len minus the ref. So if I have a memory, please set the reference inside 0, not necessarily 0, 10 to the value 11, right? And now I should be able to do this. So if I do memory.getRef of 10, it should be 11, right? Does this work? Yes. Now let's make this a bit harder. So memory.setRef to 0, 0 to value 10. I'm going to expect this to the ref of number 0 to be 10. Now I'm going to override number 10 with 10. I mean, our memory is really simple. It's going to, everything is going to just work. Okay. When I was just getting cocky, it didn't, because so why we did a index out of bounds? Why we did get that? What we get that? So why we did the index out of bounds? Where we did the index out of bounds error? So we are setting the reference 10 to be 11. Then we do 0 to be 10. We do 10 to be 10, and we get the index out of bounds. Why? Before this everything was okay, right? No? Is this random? No. So before, how? I remember this working. Oh, sorry, I didn't save this. I didn't save the file, so I don't know. I think these were okay as well, right? No. Okay, so this has a problem. Why? So 0, if I do 0, oh, okay. So because I need to actually do it -1. So the reason is, if I want to point at the last element of an array, I should, do a length -1. So 0 should do this. Now this pass, and this pass as well. So basically what we did in this commit is we added a memory that works. So sorry for the disruption again. So we basically add a memory that work both as a heap and also as a stack. We have instructions, testing inside. We have testing for our memory as well. So this is nice. This is nice. I like this. So now we can start loading stuff into our memory, the instructions. But before doing that, we should come up with actually a way of storing our instructions into the memory. So so this is important, because each this is really hard, because each segment, each memory segment chunk is a byte, so 8 bits. I can easily store the instruction opcode. I can just, this is just an enum, so I can just make this an integer, and since we have not limited number, it's going to be okay. Maybe in I think in maybe in 2 bits it's going to be okay. How many we can store in 2 bits? I think 4? No, not 4. My mathematics are rusty, so I need to actually think about these stuff. So how many things we can store inside a bit? And also, if we can do this, but the problem is with arguments. So each instruction has 2 arguments, right? Where is the instruction? Yes, each actually 3 arguments, because alt is also an argument. So each instruction has 3 arguments. So what we need that instruction, we need that memory functionality to read a chunk of bytes and then decode it. We need that, so let's add that to our memory. So what we are going to have is going to be a functionality to get ref range. So self ref or start is u64, and we are going to have also a length, which is u8, not u8, u64 also, I think. So it will return a slice of u8s. Return self that data. So start is going to be self.data.len minus start minus 1. This is going to be the start, right? So what is the end? Since it's a length, so it's just going to be from here to constant start byte is going to be this. We can remove these. So start byte plus length. It's going to return a slice. Using this, if we come up with an encoding, now we are not limited to the U8, so we can come up with an encoding to any size, but it's actually good for it to be fixed size, because you can do instructions in both fixed size instructions and also not fixed size, dynamic sized. I think there's the difference between the Intel CPUs and ARM CPUs, or not Intel, x86 and ARM. I think that's the difference. Let's actually look that up. So there was this, I think, RISC architecture. Reduced instruction set is a type of microprocessor architecture that utilizes a small, highly optimal set of instructions rather than a highly specialized set of instructions. There is also the CISC architecture, several low level. This is not necessarily what I want. Fixed sized instructions versus dynamic I know okay, I don't know, but I know that there is something. I'm gonna look that up as well. But so let me actually write this. So before we go in here, we need to do one other thing. So we need to come up with an encoding of instructions into slice of U8s, right? Yes, to a slice of U8s, and then we store that on heap. Also, and then we can actually call our CPU a CPU, because then we can do we can store this on the heap, and we can just ask the CPU, so start. Another thing is probably what we are going to do is to lock this area that we are going to store the instructions of the program. So we are going to load our instructions into the heap, and then we are going to not allow any other reference to that. So just CPU itself, the code itself should be, or our CPU itself just needs to be able to get data from that memory range. Anything else should not be allowed. So we are basically going to delete that from the heap, or we can, yes, we can do that, and we can store basically this so we can store it at the end of the memory, and we start. So if, for example, we have 10 instructions, let's say we have 10 instructions, so, and each instruction takes 1 byte. It's not going to take 1 byte, but just for the example. So if we put 10 instructions on 10 bytes at the end of our memory, we are going to start the heap memory for the program to use, for the instructions to use, from the number from basically 10 before end of the memory. Okay, so we are going to reserve that space for our instructions and not allow anything else to access that. But we are going to do that in the next video, and it's not a hard thing to do. If we do this, the encoding is actually simple because our values are just U64s, so we can use them. We can just, and they are just numbers, so we can easily map them. And also our instruction opcode is just an enum. We can just basically convert that into a integer, into a number, and that would be our instruction representation in bytes. And then we can load all the instructions into the memory, and then do have a special CPU action and memory action to load the next instruction. And finally, we did this actually. We just need to do this. We need to do these two, and then we are we have actually a real CPU, almost a real CPU. So there are tests, mostly tests, right? Memory is now both stack and heap at the same time. Test for memory and CPU. Publish this. Okay, so that is pretty much it for this video. Stay tuned for the next video. Like and subscribe if you like this content, and do the little alert button to let you notify you when I put another video. And you can always comment if I have any problems in my code, if I'm just telling anything wrong, just saying anything wrong, just tell me. You can also contact me in Twitter and mail and GitHub issues. So that is pretty much it for this video, and until the next video, goodbye.